to buy the entire series in case I didn't like it. And then I finished it, and then now I can't get the rest of the series. And I'm very sad about
that's
it.
fine.
No, I'll
Okay,
mail
all right,
that
all
to
right,
you.
look,
I feel
look.
We'll
like
figure
I
it
heard
out.
someone mention
The Hobbit
my
is a
dad.
great book, terrible movies. Lord of the Rings, great movies, terrible books.
That's a hot take right there.
I don't know if I agree with the
Bad.
terrible books yet, but I do agree that the Hobbit movies were not great, and that the Lord of the Rings movies
The
are.
best Hobbit media was the video game for the Xbox. Moving on.
I never played that.
All right, I
It
had
was
the
like my
Hobbit
very
game
first
for the
video game. It was lit.
PlayStation 2.
Well,
and-
Lego Lord of the Rings.
Alex doesn't care.
Never played the Harry Potter Game Boy games. Those were good.
You know I did.
Who did?
I did, Aaron.
Oh, yeah.
The Game Boy Lord of the Rings game?
No, Game Boy Harry Potter.
Ah, that
Ooh,
I
I-
did not play.
I played the Game Boy Lord of the Rings
Harry
game.
Are you talking
And
about
Harry
Game
Game
Potter.
Boy
Boy
Cat
Color
I had
one?
when I was a kid.
I had abs.
Yes!
That's the only one I had, and it was pretty good.
I couldn't beat like the second level though.
I don't have a Game Boy, but I'm pretty sure my dad's Atari somewhere, and I'm also sitting right next to an arcade that has Rampage.
Rampage.
No way, you have that in your house?
Yes, my dad comes here sometimes.
You'll
It has
actually-
Rampage, Gauntlet, Joust, and Defender.
Oh, my orthodontist.
All right.
Thank you for your patience, Alex.
the end of the meeting.
Yeah.
Thanks again, everyone, for coming. This week we're talking about some sci-fi inaccuracies and some of our favorite space-related media. And yeah, so hope you enjoy. It's a bit of a lighter topic this week, not as much spacey stuff. Well, not as much like real science, but we'll debunk some things with real science. Next slide, please. Yeah, please sign in, as always.
Nice.
Is the link already in the chat?
That's a good question.
Go ahead and add it. I don't have it.
All right. Perry, can you do that?
Yeah, sure.
All right, thanks. All right. Next slide. If you haven't already joined the Astronomy Club Discord server, you should definitely do that. It's a lot of fun. We have a bunch of different channels to talk about general astronomy things, astronomy memes, homework help, whatever you want to talk about, really.
So yes, e-board elections. We know it's been a hot topic recently, and you're all waiting with bated breath to hear what's going to happen. So elections are next week. Crazy, it's already upon us. And so we'll just explain a little bit how it's going to work. So we explained a little bit times, but we'll just give it a little breakdown. We'll give it again next week. So next week, all of our candidates will be having the question and answer. Well, they'll be giving their speeches. It'll be about 2 minutes each for each candidate, with around 2 minutes of question and answer as well. We'll be recording it the entire time, and at the end of the election section for the meeting, whoever's present will be able to vote. But then after the meeting, we will also be we will be sending out a Google form on our email and then on social media as well, with each of the candidates, and you can vote for each position for each candidate there. We'll also be attaching the video clips and question and answer clips for each candidate, so that the people who weren't able to make it to the actual meeting can still see who's running and still be able to vote. There's still a requirement for who's eligible to vote, so don't worry about just random people voting who have never come to an astronomy club meeting. Yeah. And so that form will be live for about a week, and then we, as the e-board, will count up the votes, make sure there's no funny business, and be announcing the winners of the election probably at the following meeting. So yeah, as for who's running, for the president position, our current PR, Henry Edmondson, is running. For the vice president position, our current treasurer, Ishita Sharma, is running. For the secretary position, our current secretary, Perry Zilberman, is running. For the treasurer, we have a few people running for the treasurer position. We have Connor Burbage running, as well as Fatin Ishraq, Daniel Ajust, and Robert Zumo. And then for the public relations position, we have Lena Weiss and Adrian Popescu running. So we're excited to see that you all are excited about the club and want to join the e-board or keep being on e-board. It's always nice when there are contested elections. In years past, we've had everyone run opposed, and while it's always nice to hear people's ideas, a little bit of competition never hurt anyone, and always just adds to the club because it pushes people to think of better ideas and just pushes the club to be better overall. So are there any questions about elections? Cool, then we'll just move on. Space news.
All right, so recently it was announced that the Space Force is going to start accepting applications on May 1st. It's only open to current military service members, and they could switch from any branch of military or over into the new space branch. They're mostly looking for people in the Air Force, though, just because the objectives kind of align more easily. It's only available for a month because they kind of just want to gauge how many people actually do want to move to the Space Force and where they're going to take it from this point onwards. And it will be a 2-year commitment for anyone who will decide to serve.
All right, and NASA announced earlier this week $125,000 in funding for a study of a new concept for a space telescope built inside a crater on the far side of the moon. It's called the Lunar Crater Radio Telescope. So it would be a radio telescope, and it would be about twice the diameter of the current largest telescope, which is the 500-meter aperture space telescope. Is that what it stands for, FAST, in China? And there are a few advantages to building this one on the moon. One of the things that makes it easier to build on the moon is lunar gravity is much, much lower than on Earth, so it's a lot easier to support a structure of this size because it weighs a lot less on the moon. It would also have no radio interference from Earth. Being on the far side of the Earth, you can see in the diagram on the bottom there, most of Earth's radio noise from television and radio broadcasts would be blocked by the moon because it's on the far side. So there would be a lot less interference when it's trying to observe deep space signals and things like that. Because a crater is already almost the right shape for a radio telescope dish, you don't need to dig out a giant hole like you would on Earth or smooth out a lot of terrain like on Earth. Craters are already reasonably smooth and, you know, sort of the right shape. They're not quite a perfect parabola, which is what you need for a radio telescope. So the way this one would work is by having a bunch of rovers positioned around the circumference of this crater, and they'd each have a wire mesh net that sort of hangs down and connects. And the rovers would be able to move on each side to sort of pull and adjust the dish into exactly the right parabolic shape to reflect incoming signals up to that suspended receiver, which you see on the red lines there, which would also be held up by rovers. So this, you know, would have less interference from radio noise on Earth. It would also have no atmospheric things to worry about. The atmosphere is mostly transparent to radio waves already, but there's always interference from weather and things like that that can create electrical signals that would interfere with the radio telescope's operations. So it's a cool study. It's definitely going to be a very long time until it's built, if it even does get built. This is only a phase 1 study of the concept, but everyone is very excited about it. Lots of news outlets picked it up, you know, as soon as NASA announced the funding for the study. And it seems like it would be a pretty cool telescope if it ever gets built.
So I have a question about this.
Yeah.
So So like about the telescope, like every now and then, like as the moon orbits the Earth, the far side is going to be facing the sun, which means the telescope will basically be pointing directly into the sun. Is there any way they're going to account for like protecting the telescope from radiation, especially since there's no atmosphere on the sun, on the moon?
I don't know. That's a good question. Yeah.
The
I
sun
know
doesn't
that
emit a whole ton of radio information, I believe. Correct me if I'm wrong. But so it shouldn't mess with a radio telescope so much. If it was a visual telescope, then it would mess it up. But I think that a radio telescope wouldn't need that much protection unless there was like a solar flare storm type of thing. But that would mess everything up on Earth too. So we probably wouldn't be too worried about that.
I think one of the things that they did mention in the article was that it would be beneficial to have the telescope pointed away from the sun for, I guess, like half the lunar cycle at a time, instead of on Earth where you'd sort of be pointed towards the sun, you know, for 12 hours every day, or sort of in the direction of the sun. If it's on the moon, then, like, you know, as the moon cycles through its lunar cycles, you'd get sun for 2 weeks out of every month, but it would be like 2, you know, concurrent weeks. So I know that was one advantage they talked about, was having longer continuous observing time without any radio interference from the sun.
All right, so some exciting news. This morning, a study was published that gave another confirmation of Einstein's general relativity. Basically, astronomers took data over the course of 27 years about a star orbiting the supermassive black hole at the center of our galaxy, which is Sagittarius A star. And the orbit that was mapped out was shaped like a rosette, as you can see with the image. And it's a really cool confirmation of Einstein's theory, because Newtonian gravity predicts that any orbit or any bound objects would orbit in a closed, in a closed loop. And that's all there was. But according to Einstein, that was not always the case. That's actually never the case, because there are orbital motions where they're causing a precession. And so the star, as you can see, would precess towards a certain direction forward in a plane of motion and cause this really beautiful shape to be mapped out. This isn't the first confirmation of this type of orbit, because Einstein, back in his day, kind of used this as an example of why Mercury's orbit is also in this kind of rosette shape, though the effect isn't as pronounced, just because Mercury isn't that massive and the sun isn't as massive as, let's say, a black hole. A really cool part of this is that it kind of strengthens the evidence that Sagittarius A star is a supermassive black hole. It's highly suggested that it is, but there is no confirming evidence that it is for sure a black hole. So this kind of just pushes it forward in the right direction a little.
All right, so today we are going to be talking about all of your favorite sci-fi movies and TV shows, and what they get right, and more importantly, what they get wrong, what's inaccurate about the science in these science fiction movies and TV shows. So I think we're starting off with Armageddon.
Yes, unfortunately. So we're going to talk about things that some sci-fi movies get right, but this movie doesn't get much right, unfortunately. So for those of you who don't know, Armageddon's basic plot is that an asteroid the size of Texas, as they love to mention a million times in the movie, threatens to collide with Earth within 18 days, and only a group of ragtag oil drillers can go and save the planet. It's before we get into what's wrong with this movie, because there are over 160 different inaccuracies that are found. It's supposedly one of the worst sci-fi movies to have ever been made, and it has so many scientific inaccuracies that NASA actually uses it as a training exercise in its management programs to see if people could figure out all of the different things that are wrong with this movie when it comes to its scientific plot. You can just go over to the next slide. So one of the biggest disgraces to science is the fact of how they plan on dealing with an asteroid that's coming at them. To even begin with, an asteroid the size of Texas, which is going to be about 1,000 kilometers wide, will be visible years before. Yes, exactly. Thank you, Catherine. CinemaSins was spot on with this. But you would see that years before it comes within that close range of Earth. Just not even thinking about that logic. Their idea of trying to save the planet is by placing a nuclear bomb drilling a hole into the asteroid, placing a nuclear bomb there, and then leaving and splitting, basically using the bomb to split up the asteroid in two, so it kind of just deflects away from the Earth. If you go to the next slide, there's actually a video which is sort of the ending scene of the movie where this happens.
Let me just turn sound on real quick. There we go.
Something's not right. Too much time has gone by.
Zero barriers about to be breached. 1 minute.
Harry, come on, press that button. We're going back and do it ourselves. Just don't. Wait 1 minute. Dan, we're about to cross the threshold. Come on, Harry, press the button.
Colonel, I'm asking you just 1 more minute.
Press the button, Stamper. Lord. Harry will do it. I know it. He doesn't know how to fail. We win, Tracy! Press it!
By 400 miles, and most of the small particles have been vaporized.
Houston, we're coming home.
We copy that, Dorito.
You, Harry. You the man.
Flawless.
Woo! Yeah, that's pretty much the ending. If you go back to the previous slide. So I haven't seen this movie because I don't want to lose more brain cells. I already have too few of them. But apparently they send the team of oil drillers to the asteroid to drill a hole about 800 feet deep and place the bomb there. There are a billion reasons why this wouldn't work, but the main thing is that any type of bomb that we've created so far does not have enough energy to do what they showed in the movie. To split an asteroid that size into two, you would need about the same amount of energy that the sun produces every second. To put it into context, the most powerful nuclear bomb that was ever built was the SAR bomb, which is about 50 megatons of TNT. The sun produces about 1.82 billion SAR bombs every second, or like the energy is equivalent to that. So there is physically no way possible that a bomb as weak as what we had at that time, or any time for that matter, could have split an asteroid into and done what it did. Not to mention that all these people who were in the spaceship outside just the perimeter of the asteroid did not die from, the explosion. The Earth was not impaled by another bunch of rocks, or just anything overall. Makes this one of the worst sci-fi movies ever. And if you want to see more wrong things when it comes to science, Phil Plait, who is an astronomer, has an article known as, where he keeps like an article journal going, known as Bad Astronomer, where he lists out one of the about 20 to 30 inaccuracies of the movie with more specific details. But again, there's over 160 of them. So going into all the details would be impossible. I know. I agree, Blair. I definitely agree.
Okay, so Star Wars. My favorite sci-fi franchise, except for the last 3 movies. But yeah, lots of cool science things, lots of cool science fiction things, but some of them, unfortunately, aren't too realistic. So we'll get into just a few of them. It would be way too long to cover all of them. So the first one is explosions in space. I like the Phantom Menace, yes. Darth Maul is my favorite character. Just play the video. So I have 2 short videos just demonstrating. In outer space. In actuality, explosions in space do happen, but they're actually a lot smaller, and they're not big fireballs like that. Explosions need like gaseous oxygen in order to burn and create that fire, and while there would be some explosion, all of that gaseous oxygen would dissipate very quickly, and so you wouldn't get that big fireball. You would actually see something more like a camera flash. Yeah, so move on to the next video and just play it. Of Alderaan in A New Hope by the Death Star. So you can just play it again real quick. That has always been my biggest pet peeve in like most space movies. And there's actually a term for it. It's called the Praxis effect, and that's actually something coined from Star Trek, where a planet called Praxis was blown up. But basically what's wrong with that is you wouldn't expect that to be a ring. An explosion like that should dissipate in every direction in space, because in space there's hydrostatic equilibrium. So you'd see more of a spherical explosion. That ring is from what we see on explosions on Earth when it goes across like the horizon, across the land. But in space, you wouldn't really see that. You might see something more like the next video. Yes, I think a spherical explosion would look so much cooler, but Hollywood doesn't seem to think so. So this is a slow-mo video of an explosion. About a minute long, but water, like space, in a hydrostatic equilibrium, basically the amount of pressure on an object from all sides. That's where the hydro and hydrostatic equilibrium comes from. And then this part's cool. You can see it start to contract.
Alec, we didn't hear a word you said over the explosion.
Can you hear me now?
Yeah.
Okay.
Seconds.
Okay. Sorry. So basically, this is more like what you'd see in space. Basically, a spherical explosion, which, like someone said in the chat, I think it would be much cooler than just a ring like Hollywood likes to show. And that's because space is in hydrostatic equilibrium. That hydro comes from water. And so you can see from this water, the pressure wave at least, and the flash of light and ball of fire, whatever, is all expanding outward in the same speed at the same in every direction, making like a sphere. So that's what it would look like more. Star Wars gets this wrong. So many different things get it wrong, but it's always been a major pet peeve of mine. Next thing. The next one is light speed and hyperspace travel. As you all know, we've covered it before. Anything with mass, so pretty much everything, every spaceship that you see in Star Wars cannot travel at or greater than the speed of light. In Star Wars, the way that ships get around, if you're not too familiar, is that they get fast enough to go to light speed, and then they're able to travel in hyperspace. And hyperspace is an alternate dimension that can only be accessed in Star Wars by breaking light speed. And in order to do that, a ship needs something called a hyperdrive. And that technology, one, doesn't exist, and it's just pretty implausible for it to happen, for there to be another dimension that can do that. we've talked a little bit about wormholes and like bending space-time, so we could do something like that, but for like an engine to basically transport you to another dimension seems pretty improbable. And there's also instances in Star Wars of ships being ripped out of hyperdrive by other ships and like crazy technology going on there. So it's pretty inaccurate. And I have another short video after this from scientists at Georgia Tech explaining a little bit why.
What does it mean to make the jump to light speed? First, let's think about what it means to travel at the speed of light. So nothing moves faster than light. Light travels at 186,000 miles per second. So let's take an example. If I want light to go between the sun and the earth, it takes light 8 minutes to make that jump. If we want to travel on a jumbo jet between the earth and the sun, it's going to take us 19 to 20 years to travel that average 93 million miles. So it's obviously a very nice idea to go at the speed of light, but there's some problems with it. First problem is we're massive. So the more we try to get close to the speed of light, we're getting harder and harder to accelerate, and it's taking more and more energy and fuel to get us up to that speed. And the clocks measure different times. So you're going to be maybe late for your battle, or you'll be too early because time is different on the ship than it is to something stationary. But here's the real problem. We're actually going to be in a galaxy far, far away that maybe it's about the same size as the Milky Way. And it takes light 100,000 years to move from one end of the galaxy to the other. So even if we're going at the speed of light, there's no way Han Solo is going to make it in time for an epic battle by moving 100,000 years across the galaxy. So what we need to do is to take those 2 points in space-time and make them closer. So we want to curve space-time. So when we put on our hyperdrive or our warp drive or whatever we're going to use to power our ship, what we're really doing is not moving faster than the speed of light. We're curving space-time, or we're using a wormhole to tunnel through it, or maybe even going into a higher dimension we don't know about yet, but we're shrinking that distance so we can move faster than it appears we can. The problem is that to curve space-time, we need something we don't actually have, which is called exotic matter, a fancy name for things we don't know how to produce. So if we could create matter that violated the laws of physics that we have today, then we could potentially build up this warp drive, fix the clocks so that we don't arrive either really old or really young for our battle, have the exotic matter get us there, and then protect the ship and ourselves from the forces that would rip us apart. And then we've got ourselves a jump into hyperspace.
Yeah, so that thing that she mentioned called exotic matter, they kind of explain that that is part of what makes it possible in the Star Wars canon, but once again, not really accurate as far as we know. Next thing. Lightsabers, everyone's favorite thing to pick on in Star Wars. So there's a couple ways to come at this. For one, people say that their lightsabers are actually composed of lasers, and if you take this interpretation, then that raises a few issues on its own. One, you would need something at the end of the beam to reflect it back and keep it from just extending on as long as it can. Two, you need something compact enough and powerful enough to power it as a power source. And then three, lasers don't clash when they cross beams. They would just pass through each other. They're also silent. Light doesn't make sound. So yeah, that's if you interpret it as being a laser. If you interpret it as being plasma kept in some type of force field, whether it be an electric field or a magnetic field, that also raises its own issues. For one, for the sake, similar to the first one, the power source would need to be way too great. And I will give some examples in a second. But another reason is if your force field, whatever that's containing the plasma, is a magnetic field, that wouldn't work because within the lightsaber it contains heat, and magnetic fields can't contain heat. You always see lightsabers cutting through things, melting metal, burning people in half. So a magnetic field wouldn't be able to contain that heat. Basically, it would just keep emitting that heat away. So Luke holding it there would probably get his face burned off. And also, if the two plasma blades were to come into contact, this would result in something called a magnetic reconnection, which just has to do with the magnetic fields within the plasma kind of rearranging, and all that magnetic energy gets converted to kinetic energy, thermal energy, and particle acceleration. And so that would cause a big release of all the plasma, and basically the two people clashing the lightsabers would get their entire bodies like burned off. For people saying that the Force is what contains the lightsaber, I challenge that, because you see people in the Star Wars universe holding it when they are not Force sensitive and using it and activating it. So, yes. So yeah, the Force, the person wielding it and using the Force is not a good enough reason. Yes, the Force is in everything, but not equally. So you have Force sensitive beings in the Star Wars universe, and they can use the Force and tap into it, but other people can't, or other living beings can't. And also in terms of some of the energy that would be required, I had it pulled up. There's actually like there's an article on Wikipedia called Physics and Star Wars, talking about these inaccuracies and some of the other ones. And it said that an incredible amount of so basically, to power a lightsaber with an electric field strength, in order to be able to hold together the laser, would be equal to 1/10 of the total energy output of the sun in 1 second. And it would also require 10 to the 11th kilogram of nuclear fusion fuel to operate for a minute. So that would be the equivalent of 10 pyramids of Giza of nuclear fission fuel in the hilt to operate a lightsaber. And so, sure, I like to think that kyber crystals are perfect and there's nothing wrong with them. And I like them as a power source, but I don't think that a single kyber crystal can contain that amount of energy. So, yeah. There are plenty of other inaccuracies in Star Wars, although one thing that about lightsabers that can kind of be possible, they're like, in terms of the lasers don't clash with their do not clash when their beams cross. There was an experiment in 1936 by Euler and Heisenberg that showed that light can actually interact with itself. It's an effect due to quantum fluctuations in the vacuum of the vacuum. And so in that way, you could get them exerting some amount of force on each other, with the photons scattering in each direction. But yeah, that amount of the energy to do that for a lightsaber would be too much, like I mentioned before. Yeah, there are plenty of other things, sound and space, but the Star Wars creators have said before, like, that's for the benefit of the audience, and that people in universe don't actually hear the sounds in space.
Okay, so I didn't just pick like a single sci-fi media. I have a few scattered around, but the first one I wanted to get at is continuing on the theme of faster than light travel. I think just about every sci-fi movie or book out there has to have some explanation of how you can travel very fast, because it's kind of inconvenient if you have to limit yourself to a single planet. You want to be able to get to different stars, and you don't want like all your characters to die off while somebody's traveling from one star to another faster than light. So Battlestar Galactica has something a little different than Star Wars. Instead of supposed light speed travel, they have the warp drive, essentially, which we talked about, that by bending space, you can travel a shorter distance through it. and then that actually works. You don't have to violate any physical laws that we really like. So there's some kind of funny things about it, though. It has a few different names. It's got the jump drive, the FTL drive, which I couldn't find anything that acronym stood for. The temporal warp synthesizer, going along with warp drive, and the quantum jump core. And again, as much as I looked, I couldn't find anything that related to quantum mechanics here. I think that's just kind of a buzzword that that in a lot of sci-fi, people like to throw this in. Temporal and warp are another one, but the warp drive, actually, we discussed that kind of works. So the basic idea is sound. You fold space in front of you, and then you can travel through it without violating any principles, and basically travel faster than light that way. Now, in the Battlestar Galactica lore, they kind of go a little more in depth with that, which is, I feel like, kind of a rookie mistake with sci-fi. You know, if you don't explain your things all too much, you can kind of get away with a lot. But if you really try very hard, you start coming up with stuff that really doesn't make sense. So here, what they do is they create artificially a fourth dimension, this temporal matter, which surrounds your ship as it travels, and that creates like a corridor of temporal matter that you can travel faster than light. And while a fourth dimension already exists, it's time. You know, things have like a height, an X and a Y location, and also a time coordinate. So there's no fourth dimension really to create if we're trying to come up with a warp drive. So that's kind of a silly explanation that they have there if we're going to nitpick at it. And then the addition of temporal matter, whatever that's supposed to mean, you know, it's like we started off with an idea that was pretty good, and then we just kept digging, and you know, what they're coming up with now is just, I don't know what's going on there. Last thing I want to nitpick about this is the animation of the ships. So in Star Wars, you know, even though we already said that their hyperdrives are kind of preposterous, but at least the idea is they're moving forward, and the animation looks like the ship moves forward in it. Here, the ships seem to just like sparkle a little and vanish, and I guess maybe that makes sense. If they're going so fast, you don't really even see them; they just disappear from the frame. But it almost looks more like a teleportation than an actual movement in a direction. All right, next slide. So again, continuing with sci-fi travel is a real-time strategy game called Supreme Commander. This one I imagine less people have heard of than Battlestar Galactica, but it's a really good game. I recommend it. So the premise of this game, at least part of the premise, is that humanity discovered quantum gateways, which lets you basically teleport to distant worlds. So here, rather than moving really fast and having to violate the speed limit of the speed of light, we're just teleporting. Again, I think they like using the physics buzzwords like quantum and just like, what are we going to call it? Quantum gateway. But, you know, there's actually maybe some merit to that. We discussed in our meeting about our favorite ways to die in space. One of the options was quantum tunneling into the sun, and so that's an actual thing. Quantum teleportation is a thing, but I think that refers actually more to moving information faster than light, rather than actually transporting matter faster than light. So this idea of quantum gateway and using that word actually kind of works here. And they don't make the rookie mistake of over-explaining things in this game. It's just kind of like, well, quantum gateways exist, and we're going to leave it at that. So there's not a whole lot more to nitpick. It just kind of seems like a sort of reasonable idea. You know, you could argue how practical or easy it would be to quantum tunnel, you know, an entire like giant mecha in such a precise way. But you know what? There's something to it. The place where this sort of falls apart a little bit, again, I'm going to say in the animation. Unfortunately, I couldn't find a GIF of it, but the background here is kind of what the animation looks like when you're teleporting, when you're quantum gatewaying, and it looks a lot like the hyperspace in Star Wars, like when they're actually in hyperspace and you have this sort of like spirally, like weird stuff that doesn't look like stars anymore. That's what it really looks like to me. And again, that kind of gives the impression of moving in a direction and not so much teleporting. So both of these, they just mix things up. And at that point, I just can't buy it. All right, next slide.
Right, so we're going to talk about the MCU a little bit now. So first thing we're going to talk about is PIM particles. So if you don't watch the Marvel Cinematic Universe too much, PIM particles are essentially particles that allow someone to grow and shrink and also change their density and their mass, and it also lets people time travel. And I don't think that's, I don't know how that works or how that would work at all. Because if you're gaining or losing mass, that takes energy, and there's no energy coming into the system. So you have some conservation of energy problems there. Also, if you don't watch the MCU too much, there's some scenes where something that grows or shrinks keeps a lot of its properties. Like, for example, you have someone grow quite large, but they also don't like explode or something, or don't collapse under their own weight, which is odd. Yeah, PIM particles just make absolutely no sense.
Twist is simply the lighting support.
Yeah. Okay, so also, this isn't exactly sci-fi, but we should probably talk about Captain America's shield, because that doesn't make any sense. So some of the times it absorbs all the kinetic energy that hits it, and sometimes it also redirects energy from blows, which aren't really consistent with each other. But one of the main things is that conservation of energy. So if it absorbs all the kinetic energy that hits it, the shield should get very hot, because that energy has to go somewhere, and it would go into the heat of the shield. And apparently, I read some articles, and if you assume the specific heat of Captain America's shield to be similar to that of steel, after it absorbs fire from like a machine gun for a few seconds, it would heat up to like 1,000 degrees about, which is not very good for Captain America.
Yeah, but that doesn't take into account the
He has the super soldier serum.
Vibranium dissipates kinetic energy, so it wouldn't heat up.
But does it absorb or I read that it absorbs kinetic energy. And if it dissipates it, it has to dissipate it somehow. Because the energy can't just disappear.
Yeah, even if it does dissipate it, it'd have to probably dissipate it into heat that it would then radiate into the wielder of the shield and the air around them.
And then they would fry. Yeah. Also, I don't have a slide on this, but just another pet peeve about the MCU with Iron Man. So there's a lot of scenes of Iron Man in the MCU where he's just going like 100 miles per hour or something, and he just stops, where he gets hit really hard and he goes flying, and then he just hits a building and he just stops. And I'm pretty sure he would die every single time, because F equals ma, force is equal to mass times acceleration, which means that if you accelerate a lot, which is what happens when you go from like 100 miles per hour to 0 really quickly, that would impart a huge amount of force on Iron Man, on Tony Stark. I don't think that's survivable. But yeah. Anyway, that's this slide.
Hey, Al, you're muted.
Thanks, Alex. So another sci-fi universe that I really enjoy and I'm going to recommend very strongly is Futurama. Now, of course, Futurama is a comedy and nothing about it is really supposed to be accurate. But there are some things I wanted to discuss again. One of them was, once again, space travel. So Bessie is the ship the ship that the main characters in Futurama use, Planet Express's delivery ship. And it can travel at 99% the speed of light. Now, this is much faster than the traditional speed of light, because in the year 2208, the speed of light was increased. Just for anyone who isn't aware, Futurama is set in the year 3000. So I guess, physicists decided to increase the speed of light somewhere in between because it was just too inconvenient. Furthermore, it doesn't actually move. So this ship is still much faster than other ships in the Futurama universe. And the way it works is that it actually moves the universe around it rather than moving itself. Why that lets it go faster, that would be a very good question. Furthermore, it's powered by dark matter, which conveniently the crew can access by their pet Nibbler, because Nibbler poops out dark matter. But later on, it turns out that it's not a very effective fuel source, so they switch to whale oil. Also, the ship gets 200% fuel efficiency. I guess they're not limited by 100% either, just like they're not limited by the speed of light. All right, next slide. So one more thing about Futurama. Oh, you guys can watch the video and then I'll...
Yo, old guy, why do we have to use those tiny micro droids? Can't you just shrink us?
Oh my, no. That would require extremely tiny atoms. And have you priced those lately? I'm not made of money. Leave me alone. Me next.
So I just wanted to add this in here because in the context of Marvel and Ant-Man being able to shrink, in Futurama, there's an episode where they have to shrink down because one of the characters has a parasite, and so they need to enter his body to fight off the parasites. And so rather than just shrinking themselves, because that requires very small molecules, which are very expensive, they just use tiny robots. So Futurama's really got the good sci-fi explanations. Very accurate and really funny show. You guys should all watch it. All right, next. Okay, and one other, back to Battlestar Galactica, something that I wanted to point out, which I actually really appreciate in the show, so more on the side of accuracies than inaccuracies, is how the ships are able to maneuver. So if you look at like the space fighter combat in Star Wars, they're doing all these maneuvers just kind of inexplicably, and they fly around like fighter jets in an atmosphere, but when you're in space, that kind of doesn't make a whole lot of sense. But in Battlestar Galactica, you actually see, it might be a little hard to see in the GIFs here, but you might notice that aside from like the main thrusters on the back of these ships, there's like these little jets just like around the entire hull, and that lets it kind of go around in any what direction you really want. So it's not just kind of wobbling around for no reason in no atmosphere. There's actually kind of an explanation for that. So bonus points to Battlestar Galactica for that. Next slide. And I think this is the last of what I've got to say. Another sci-fi, a book this time. Well, actually, they made a movie, but I never watched it. But the book Ender's Game, which again I will recommend, has a space station in it where they describe, yay, someone likes Ender's Game. So the book's really good. You guys should read it. They have a space station in it which has artificial gravity, and in most other sci-fi media where there's artificial gravity, it's kind of like an on-off switch that has like just some inexplicable source of gravity. Whereas in the space station, it's actually basically cylindrically shaped and it's rotating. So if you're standing on the edge of it with your feet pointing away from the space station, so like out into space, you would basically feel a centrifugal quote unquote force. Obviously comes from the real centripetal force. And so you would feel gravity. I don't know if any of you have ever experienced or seen like these like amusement park rides that just spin very fast and you get like stuck on the wall. That's basically how that would work. There could be a few concerns with this, like having a structure that is secure enough to not fall apart from that rotation. But it turns out that the strength of that structure wouldn't be that much more than you would need already just to support like atmospheric conditions within a space station. So that's pretty sound. It's not unreasonable to have something like that. And another little addition to this is that, so this space station is to prep kids to become like battle generals, things, something like that, basically. And so they have mock battles in the center, where since the rotation is less, there's basically zero gravity. So that's just kind of like a really well thought out thing, I think, by an author who isn't a scientist at all, but actually thought of how this stuff could work. And this was written back in 1985. So before when the e-board met, we were talking about different places where something like this exists, but this was written quite a while back, I think. So yeah, points for Ender's Game.
Sorry, I just needed to refresh it really quickly. I think we changed one slide. Yeah.
So yeah, Back to the Future is flawless. No further need to discuss. No, there are a few things. For one, hoverboards. Right now, it's not a possibility, but I'm sure at some point we could probably figure it out. Thank you, Alana. Thank you. With things like hoverboards in sci-fi, and with a lot of things in sci-fi, they kind of push technology in certain directions. Like, we try to fulfill those things that we've seen in sci-fi. Like, cell phones were like originally something from Star Trek, or like Zoom calls were like, I remember watching the Jetsons as a kid, and I was like, I can't wait for us to be able to like have TV stuff, like phones, like TV calls. I just thought that was cool. So hoverboards, they can't exist now. I don't really know how they would exist, but hopefully we'll get them in the future. I mean, we have things that can hover, like light speed rails and those magnetic rail trains. So it could be something like that. Self-tying shoelaces, probably not. You could just, I don't know, just use Velcro. Who ties shoelaces anyway? So yeah, maybe that's something we'll try to invent. Flying cars. Yes, they did make these shoes. Nike did make them for, I think, like the 50. It couldn't have been 50 years. I don't know. A certain anniversary for when the movie came out.
It might have been 30th, because that was only in 2015, because that's when part of
2015
plays. I remember just it was Marty McFly that year.
Yes.
Yeah, like 2015 was when Back to the Future said like we were supposed to have all these cool things.
Mm-hmm.
Yeah, they made a fake trailer for the Jaws that was Jaws 19 or whatever that was featured in that movie. That was fun.
Flying cars.
2015.
I don't think that we're right now heading in a direction for that. I think right now we're just trying to develop self-driving cars, which I think is a more feasible direction for technology right now. Flying cars, you definitely have to develop an entire infrastructure before you even start allowing them to fly. And we know how bureaucracy works in the United States, so I don't think that would ever happen. Maybe another country would figure it out before us. But and then time travel, plenty of time travel things. We don't know how time travel works. Probably wouldn't work by getting a car up to 75 miles an hour. Yeah. Back to the Future, very fun. Tried to predict some things. Predicted that Disney would be owned by Star Wars, which is pretty funny, pretty accurate. But yeah, Back to the Future.
That, I'm pretty sure was fake.
What?
I'm 90% sure whatever that was going around was fake, because I looked up the original clip after that happened, and that's where like the Jaws was.
Oh, okay.
Unfortunate.
Then The Simpsons still reign supreme on predicting things.
All right, so now on to our other sci-fi juggernaut besides Star Wars, Star Trek. And Star Trek The Next Generation, the logo here, because that is, of course, the best Star Trek series. And you can also see from my background here, I am on the deck or the bridge of the USS Enterprise D from Star Trek The Next Generation, the best Enterprise, of course.
Wait, what is the D
And
for?
they're just numbered in order. Like the first one was NCC 1701, then it was 1701 A, B, C. So D is the fifth Enterprise.
Oh, they named multiple ships the Enterprise?
Yeah. There were 5 Enterprises, I think, so far. Yeah, and of course, there's no way we can get through all of Star Trek's sci-fi accuracies and inaccuracies, because I looked it up and there are 736 episodes across all the Star Trek series, as well as 13 movies. So there's no way we could cover all of that in one meeting. But starting off with a few things Star Trek got right, a lot of technology, they actually predicted pretty well. The first one being communicators. You can see on the left there the communicator from the original series, and later flip phones were actually modeled after the design of the communicator from Star Trek the original series. That design where it flips open and then you can talk into it, and it's wireless remote communication was inspired by Star Trek, and their prediction was right. And then later in Star Trek The Next Generation and on, they had comm badges, which are a little badge right on your shirt that you could just tap and talk to people. So those are almost like Bluetooth, earpieces or communicators that we have now. So both of those are pretty accurate. Also, laptops and tablets, they got pretty close to what we have now. Star Trek The Next Generation, I think, was the first time we saw either of these technologies, and that came out in 1987. So you can see on the left there a little touchscreen tablet, and the iPad was the first major consumer touchscreen tablet, and that came out in 2010. But I looked it up, and the first touchscreen tablet of any kind didn't come out until 1988, which was the year after Star Trek The Next Generation. And even that, you couldn't touch with your fingers. You had to use a special stylus. So Star Trek was pretty far ahead on both of those. You can see, for comparison, this was the most portable computer that existed in 1987 when Star Trek Next Generation came out. So they correctly predicted the size of laptops getting much smaller, but not quite as thin and small as they are today. But both of those predictions are pretty good. And then we've already talked about warp drive a few times in previous meetings and earlier in this meeting when we were talking about Star Wars. So I'll just mention it here briefly again, talking about the Alcubierre drive. We talked a bit about the physics of that last meeting, sort of creating a bubble of normal space and sort of a shell of warped space where you're shortening the distance of space in front of you and expanding the distance of space behind you to make it so that you can travel faster than light by changing the distance so that you're not disobeying the laws of physics. And I think the most interesting part about this is that the Alcubierre drive was directly inspired by Star Trek's warp drive. It was called the warp drive all the way back in the 1960s, and Alcubierre was just inspired by the name. There was no explanation of how this technology really worked. He was inspired by the name warp drive because it sounded like you were warping space. So, he came up with the equations and figured out how we could do this physically, even if the technology still doesn't exist, unfortunately. All right, now on to the transporters, one of Star Trek's other famous technologies. And interestingly, the reason Star Trek came up with transporters was because it was cheaper to do the special effect for transporters than to film scenes in a shuttlecraft every time they wanted to go down to a planet. So to cut down on the number of sets they had and the amount of filming they had to do, they created this concept of transporters just out of filming necessity.
In Star Trek, the transporter moves you from one spot to another, saving on shuttle fuel and special effects budgets. In universe, it's the safest way to travel. Yes, sometimes 2 guys die horrible mutilated deaths under rare circumstances, but trillions of individuals transport to work every morning without a hiccup. But what if the transporter isn't as safe as claimed? What if the death rate isn't almost nothing %, but 100% because the transporter is a suicide box? First, how does the transporter work? There are technical manuals with pages and pages of hilariously over-specific details that yet say so little. Star Trek is nothing if not consistently inconsistent, but taking the most common elements, first the transporter scans you down to the quark, takes apart your atoms, and sends the pieces of you to the destination for reassembly. But is it you on the other end, or a copy that thinks it's you? Well, who is you? That's a hell of a big question, but let's try to be good scientists about it. We don't assume there's a magic part of you that can't be measured. After all, if it can't be measured, that means by definition it can't affect anything. So Occam's razor it away and we take you as you seem to be, a collection of atoms arranged to think they're you. And because the arrangement of atoms in post-transport you is exactly the same as pre-transport, you must be you. Case closed. But you might still have this nagging feeling that your experience of stepping into the transporter will be a funny sound, a bright light, then nothingness eternal, while down on the planet a brand new life, complete with all your memories up to the moment before your death, popped into existence and assumed it's you. How could it otherwise? It lives a life as short as the mission, and a new creature with the memories of you both makes it back to the ship. If true, multiply this by all the life forms in all the ships in all the star systems, and this transport technology is a silent holocaust, which makes an average episode of Trek rather grim watching, and it's a small mercy when a crew member takes the turbo lift rather than site-to-site transport. But again, the measurements check out, so perhaps we're being paranoid and we're already late for our holiday on Ryza, so just step inside already. But atom reassembly is the optimistic version and can't be how the transporter really works, because sometimes accidents combine two crew into one or split one into two. There aren't enough atoms in you to make a second you, so the transporter has to be turning atoms into energy and energy into atoms. You are destroyed, used to charge a battery, then recreated anew. This really seems like death, but
yes, so, talking a bit about the philosophical implications of the transporter, it might or might not kill you and reproduce an exact copy of you that's not really you. But talking about some of the physical limitations of the technology, so if the transporter is converting you into energy and then back into matter, how much energy would that be? So if we take an average, mass of 62 kilograms for a person and use Einstein's equation, E equals mc squared, we get an energy of 5.6 times 10 to the 18th joules, which is about 90,000 times the energy of an atomic bomb. So that's a lot of energy that this system would have to be storing. And we know that it's not some kind of like instantaneous transmission, because there are a couple of episodes of Star Trek where someone intentionally leaves themselves inside the transporter for years or decades. So somewhere that energy is being stored inside this system, and that would be quite a lot of energy to store. So with the highest energy density battery that we have today, which can hold about 160 watt hours per kilogram, you would need a battery that weighs about 10 to the 12th or 10 to the 13th kilograms. So that would be a very big battery. It would be about 10 to the 7 times the giant battery system that Elon Musk built in Australia for their power grid. So what's that? Like 10 million of those battery systems is how much energy it takes to store one person. And then when you think about the ship, being capable of transporting dozens of people at a time, that's quite a lot of energy that the ship has to be able to store as some kind of electrical form or whatever they're storing you as, and then recreate somewhere else. So that's quite a physical constraint on the transporter. All right, now moving on to a fun bit of sci-fi in Star Trek that does not involve anyone dying. Is the Picard maneuver. It's a battle tactic that Captain Picard, who is the best captain in Star Trek, of course, came up with in a fight. And basically the way it works is by jumping to warp speed, which is faster than light, towards the enemy ship that you're fighting, so that you create a double image of your own ship, which would confuse the enemy ship scanners. So just to see what that looks like in action, here's a video clip.
Lock on tractor beam.
And unfortunately, it didn't work on Commander Riker because he already knew the Picard maneuver. But let's just watch it one more time to see what happens. So you've got your original image of the ship. the ship jumps to light speed. You see the ship traveling forward, and then you see the new image right in front of you.
Lock on tractor beam.
And it's pretty cool because they actually almost got this right, and it would have been really cool if they did get it right. So it's a little annoying that they didn't. But so here's a quick explanation of how this would actually happen. So if you have your ship that's going to jump and do the Picard maneuver, starting at the top of the screen here. Let me turn on the pointer so you can see. So this is the ship that's going to be jumping to warp, and this is the ship that's going to be staying stationary and watching. And the way I'm going to do this is the ship on top isn't going to go straight towards the bottom ship, because then it would sort of be like hitting the photons in front of it, and I don't know exactly what would happen if you crash into photons that have already bounced off of your ship's hull. Might create some kind of light sonic boom, if that can happen. So to get rid of that problem, we're going to have the ship traveling at a small angle towards the other ship, but we're going to say that that angle is small enough that we can approximate it to 0 so that we don't have to do any trigonometry. So we're going to start at position 0 here, and this is at a distance of 0 light seconds from the starting position. So if you think of a light year as the distance it takes light to travel a year, a light second is the distance it takes light to travel a second. And we're going to say that this ship is going to light speed and it's traveling at 2 times the speed of light. So position 1, 20 light seconds. Position 2, 40 light seconds. And position 3, 60 light seconds. So we're going to say there's a total distance of 60 light seconds between these two ships. So now if we look at a timeline of what would happen here. So the ship starts here at position 0 at 0 seconds, and then it goes to 2 times light speed. So in 10 seconds, it's traveled a distance of 20 light seconds. At 20 seconds, it's traveled a distance of 40 light seconds, and at 30 light seconds, it's traveled a distance of 60 light seconds, and it reaches the second ship. So then at 30 seconds, we see the ship at position 3. We're just going to say that that's close enough that the light travels instantly between those two. So you see the light bounce off the ship and go to your observer ship here. So you see the ship here at 30 seconds. Now at 40 seconds, so the ship is at position 2 at 20 seconds. And then the light bounces off of it. It has to travel a further 20 light seconds at light speed, so that takes another 20 seconds. So 20 seconds ship travel time plus 20 seconds light travel time, 40 seconds before you see the ship at position 2. 50 seconds, same thing, 10 seconds of ship travel time, and then 40 seconds of light travel time. So 50 seconds, you see the light from the ship at position 1, and then at 60 seconds, you stop seeing the ship at position 0. So basically what would happen is you would see both images at the same time. You'd see the ship in the background and you'd see the ship right in front of you. But what would actually look like is happening is you'd see that ship travel backward towards the original position and then disappear, because you're seeing the light that's bounced off the ship as it's closer to you before the light further back. So if we go back and watch that clip one more time, what would actually happen is that warp speed that you see would actually happen in reverse. That blur of light that happens would be in the opposite direction. Instead of seeing the ship come towards you, you'd see it appear in front of you, and then it would look like it's moving backwards, and then it would disappear from the original position. So it would be a pretty cool effect, and they almost got it right, and it would have been pretty cool if they did, but not quite.
All right, so in terms of more recent movies that are quite accurate, Interstellar definitely is one of the big ones. There are different parts of Interstellar that are very accurate to science. There's actually books on it. Well, there's one major book, I think it's by Kip Thorne, The Science of Interstellar. I don't have it, but I think Henry does. But it kind of details the different scientific aspects of Interstellar. And one of the major ones is the time dilation that is shown on Miller's planet, which is the planet that's orbiting the black hole Gargantua. I do love that movie a lot. So if you go to the next slide, you can see a quick video on time dilation that explains it really well. Yeah.
Einstein suggested that massive objects like the sun didn't pull bodies like Earth with a mysterious, inexplicable tug, but rather curved the fabric of space-time around them, forcing Earth to fall down into this steep valley. A highly simplified analogy is the dip in a trampoline made by the of a bowling ball. If a marble were placed on that trampoline, the marble would immediately roll towards the bowling ball in the center. This is also true for Earth's gravity. We are pinned to the ground because space, so distorted by the Earth's mass, pushes us down from above. However, the slump in the fabric around Earth is not uniform, and Earth's gravity grows more intense as we move towards its center, where the curvature is at a maximum. Therefore, like the marble on the trampoline, an object that falls towards the Earth accelerates as it races towards the center of the planet. It falls faster when just above the surface than it does, say, when it is slightly above the atmosphere. But hey, according to special relativity, the faster you move through space, the slower you move through time. This means that time runs slower on Earth's surface than it does above the atmosphere. Now, because different planets have different masses, and thus different gravitational strengths, they also accelerate objects at different rates. As we have learned, this means a variable passage of time. This is what happens in the movie Interstellar, when the protagonists land on a planet in the proximity of a black hole. The gravity on the planet is so severe that 1 hour on the surface is equivalent to 7 years on Earth.
All right, so they showed it really well. In the movie, the people on Miller's planet only experienced time passing by about roughly 3.5 hours, whereas the people that were still on the spaceship, if you go back to the other side, Henry, they, I think, had a time span of 23 years that passed by, and they aged and they experienced all these different things. And it's one of the cool aspects of it that really showed time dilation for what it was. Of course, there was some creative leeway. Time dilation of that effect would not necessarily be possible because the planet would have to be traveling at about 99.99% of the speed of light. So it'd have to be really close to the black hole. And if you think about it in like a physical sense, the black hole would have ripped the planet apart by tidal forces. So it wasn't a very stable planet to begin with, and it's not very likely that it would exist. But again, it's a movie. There's creative leeway happening. Another amazing thing that Interstellar did was how it showed a supermassive black hole. And we recently got the first image of a black hole, and it kind of, you know, is the same exact thing we were expecting as was shown by simulations. What happens is that the black hole, the back side of it, there's extreme warping because black hole's gravitational field is very intense. So you see the back side kind of projected as like a circle. It's of course more complicated than that, but it was beautifully shown in the movie. It's very accurate. I don't know if it's 100% there, but again, the physicist Kip Thorne helped develop a lot of the physics aspect of this, so it did hold up to scrutiny. Of course, there were still slight errors, but that's expected. But again, black hole image, very cool.
All right, I think that's all of our sci-fi accuracies and inaccuracies.
Does anyone want to fight any of them or have anything to add? Or
Interstellar is a stupid movie.
It was
I mean,
really
we're
boring
doing
to
90% of the fighting in chat, so we're fine.
It's like 3 hours long, and it could be like 1 hour.
Okay, yes.
But then you wouldn't
And
have time for
also,
all that music by Hans Zimmer.
Love transcends time and space. Matthew
Okay,
McConaughey has to
if
go
you
through the fifth dimension to be a ghost to tell his daughter how to do physics so she can save him. God fucking damn it, that movie's retarded. I hate it.
I hate Matthew McConaughey. He's a terrible actor.
But what about the Martian movie?
way
I
the
know. I thought it would have been
Martian's a great
funny
movie.
to see
The
that.
Martian's pretty good. I like The Martian.
The Martian is great. But like
Oh,
Interstellar,
but they didn't even simulate having lower gravity on Mars in that movie. Therefore, it's terrible.
Oof.
Yeah, but Matt Damon grew potatoes and shit. Like, come on.
No,
What more do you
that
want?
one was accurate. Game Theory did an entire video on that. Why that is accurate.
I thought you had to filter out the poop so it don't disease your potatoes.
Potatoes.
And he would have diarrhea of the mouth.
Verbal diarrhea.
Yeah.
Why would you say those words? It would cost you $0 not to say those words.
Yeah, well.
It anyway.
Oh yeah, another Star Wars inaccuracy that which isn't an accuracy, but I really like it anyway, is how they like turn on and off gravity inside of ships. I've always just thought that that's pretty neat. There's no way that you would really be able to do that, but I've always liked it. I'm a big Star Wars fan. I wasn't criticizing any of this stuff. I was just pointing out inaccuracies. Like I like lightsabers. And all those.
I don't know. It sounded like you were criticizing the sequel trilogy.
Oh well, those are awful. That's fair.
Sequel
trilogy. That's not my canon.
Listen, no, the only thing that's canon out of those new movies is Rogue One. Okay, fight me.
Yeah, hashtag not my canon.
I love Legends.
We're part of the prequel gang over here.
I'll keep extended.
Yes, prequels.
Justice for Star Wars.
Episode 3 is a masterpiece.
Yeah, it totally is. I love episode 3.
I haven't seen the prequels. I haven't watched the first 6 movies in so long.
Now that I'm home, my brother and I have just been like nostalgia rewatching stuff. Like I mentioned Lord of the Rings, the beginning of this. We watched the first 3, like all the prequels. It was lit. It's a good time.
I've just been watching
They hold up. Thank you.
The guy from
I would watch those, but I don't want to give any more money to Disney, and I don't want to get weird viruses from pirating websites.
That's fair.
What do you have against Disney?
They made the sequels, man. Like
sequel trilogy.
They're
What more
a
do you
terrible
want?
corporation.
Yeah.
Yeah.
Fair.
Listen, the only thing we like about Disney was our childhoods. Okay, everything else burn in hell.
Really? I was a Boomerang and Cartoon Network fan growing up.
Yeah, true.
I only got into Disney recently with like Moana and stuff.
Oh, Moana's good.
I haven't seen Moana.
Moana.
I really like the
I
music.
watched all the memes from Moana.
I've seen about every single Disney movie that exists.
I have all of the classic Disney movies on VHS, and I watch them semi-regularly.